Welcome. In the next module, we will be looking at solar radiance, albedo and the Arctic. Let us look at what are the challenges we face. The first one is higher temperature of earth can be attributed to greenhouse gases. This is a standard statement you will listen from many people. How accurate is this statement? How do we prove it? So this is one big question we have to answer. What factors are contributing to higher temperature of earth or the poles? Is it a single parameter or a multi-parameter? Are they dependent, independent or interdependent? What is surface energy balance? How do we measure it? Why it is important? Can we build a model to look at how the entire process are interrelated to each other? Maybe a hierarchical model or a general circulation model? Is the heat transfer a near surface phenomenon or mid-atmosphere? What are the roles of moisture, wind direction, ocean circulation, sea ice, etc. in Arctic amplification? So this is a new term we will be looking at, what is called Arctic amplification in the coming modules. What are the horizontal and vertical heat transfers that are occurring? So these are some of the questions which we have to answer now. Let us look at the basic thing, which is solar irradiance or solar radiance. So what is solar radiance? Solar radiance is the power per unit area, that is surface power density, received from the sun in the form of electromagnetic radiation in the wavelength range of the measuring instrument. So this average annual solar radiation arriving at the top of the atmosphere is about 1361 watts per meter squared. See, there are many models that are developed to measure the solar radiance. There is still inconsistencies. The reason is, let us look at the inconsistency due to an instrument, because the instrument should be stable and it should measure continually, because if there is a gap, then we may be missing out that solar radiance for during that period of time. So instrumental stability is very important. And then place of measurement, for example, whether we are measuring it on the earth's surface or it is a space based one, that is like a satellite one, or an airborne, which is like a balloons. And what about the global warming? So these are some of the factors which affect the measurement of solar irradiance, because global warming increases the temperature retained by the surface atmosphere. So that means whatever the sun rays which are entering the atmosphere and reaching the earth may be having some additional information or the additional heat due to this global warming. So these are some of the factors which are interrelated to each other, and we need to know how these things can be separated and we can actually accurately measure solar radiance. Then again, earth has atmosphere and surface. So both of them absorb and scatter solar radiation. If the measurement is earth based, then we will miss out all the reflected light from the atmosphere. So NASA's earth observing systems, solar radiation and climate experiment source provides precise measurement of total solar irradiance, solar spectral irradiance. So from this we can actually measure what is the solar radiance we are receiving. Let us look this in the pictorial forms. In our solar system, the sun emits solar radiation which reaches our earth. Once the solar radiation reaches the earth, it interacts with the atmosphere, which plays a key role in modifying the amount of energy reaching the surface of the earth. The atmosphere scatters and absorbs sunlight, reducing direct solar radiation and creating diffused radiation. Solar irradiation, that is the amount of solar energy reaching the surface, is influenced by several factors, both in space and on earth. In space, irradiance depends on the distance from the sun. This also depends on the 11-year solar cycle, distance and cross cycle changes. The solar cycle, marked by fluctuations in the number and the size of sunspots, solar flares and coronal loops, which directly affects the amount of solar radiation emitted by the sun. The solar phenomena are linked to changes in solar irradiance and impact the Earth's climate system. The solar radiation is scattered by air molecules, dust and water droplets spreads in sunlight in all directions. When the solar radiation hits the cloud, it actually passes through the diffused solar irradiance and it reaches the atmosphere. The clouds further enhance the diffusion, reflecting and absorbing sunlight and can significantly reduce the intensity of direct irradiation. At the Earth's surface, irradiance also depends on factors such as the angle of sun, that is the tilt of the measuring surface, the height of the sun above the horizon, and atmospheric conditions. These variations in irradiance influence biological processes including plant photosynthesis and animal behavior. This affects the ecosystem, agriculture, and overall environmental dynamics. So let us look at the solar irradiation reaching the Earth. This actually depends on the shape of the Earth, that is the spherical shape of the Earth. So here the equator actually receives the maximum amount, that is 100% compared to the poles, because poles are far apart. When we look at the sphere, we have a sphere and the central is our equator and the top is the pole. So this one is directly above when the sun is directly above the equator receives 100% of the sunlight, but this top part, which is the pole, receives only 40% of the solar radiation. And the tropics, when we talk about it, is between 0 to 23.5 degree latitude, it receives close to 100%, that is 90% of the energy is received compared to the equator. And the mid latitude, that means up to 45 degree both direction, north and south, roughly receives 70% of the solar radiation with respect to, if we assume equator receives 100% of solar radiation. Similarly, the tilt of the Earth and seasonal variation also affects the amount of solar energy received by the Earth. Here, the areas within the tropics actually receive more or less continuous solar radiation throughout the year, but the poles either receive maximum sunlight during the winter or no sunlight during the winter. So this is how summer and winter have different extremes of solar radiation reaching the poles. Similarly, Earth orbit, because it is not a perfect circle, so we also have a difference due to the Earth's rotation. So since the Earth orbit is elliptical, the magnitude of the solar radiations at the Earth is least when the Earth is farthest from the sun and greatest when the Earth is closest. Similarly, the angle of solar illumination with the increasing latitude reduces the average solar irradiance by an additional 1/2. So these are all the factors which affect, and of course atmosphere, which has dust, water vapors, clouds, etc., also play a vital role, because when there is cloudy, not all the 100% of the sun rays reaches the Earth. So there also we have different amount of energy that is received by the Earth. Let us look at the peak energy received at different latitudes. So here, this is a graph which actually shows the solar energy received at local noon, that is 12, each day of the year, which changes with latitude. So we can see here, this top part is the equator. So here we receive roughly 100% of the solar radiation that is coming on these areas are being received, but the number becomes very less in the poles. So if you look at the equator, that is the gray line which we are looking at, this receives more or less, if you look at that, it is very close to 100% of the energy is being received during this equator throughout the year. But when we look at northern, that is the blue lines, here we see this is the blue line, 60 degree north when we look at. So in the month of January, it actually receives very less energy. So this is the y-axis is the energy graph. So this receives, equator receives the maximum energy, whereas the 60 degree north receives minimum energy during the winter month, that is January. And in this end, if you see November and December, they are receiving less amount of solar energy. And at the same time, if you look at the southern region, so June and July, they actually receive the minimum most energy. That means that is winter for the southern hemisphere. So 60 degrees south receives the minimum amount of solar energy. So this way we can actually see the peak energy received at different places like poles and other places keeps on changing throughout the year. And here we can actually look at how much of the energy that is received. So the top one is called is the Arctic Circle, and the bottom one is the Antarctic Circle, and the central part is the equator. So if you look at the equator, the pink line, so if you look at the 0 to 40 is the amount of energy, solar energy received by that particular region. So this always remains in the close to the 35 range. That means maximum amount of solar energy is received throughout the equator. But if you look at the Arctic Circle, 0 means they don't actually receive any solar energy during this time. That means January and February, if you look at this dark black spot. Similarly, from September or October to December, this time also it is the winter in the Arctic Circle. So those periods are basically black. In other words, there is no solar radiation received by these North Pole during that period. And if you look at the South Pole, it's Antarctica Circle. So from March to basically up to September, those 5 or 6 months, if you see, there is a zero solar radiation. That means this Arctic Circle does not receive any sunlight during this period. So this way we can actually see where there is a maximum sunlight received. And in fact, if you look at the Arctic Circle, during the period, let us say from the month of May to July, they receive the maximum sunlight here. And if you look at the South Pole, that is the Antarctic Circle, in the month of January and from the month of November to December, they receive maximum sunlight. So if we go a little bit more into solar irradiation in the Arctic, so getting solar radiation data in the Arctic is very challenging. Why? Because the main reason is unavailability of weather stations having pyranometers. These instruments are expensive and also this requires regular maintenance. If you look at the North Pole, it is most of the time covered with ice and it is very cold there. So that means people cannot reach that place quite often very easily. So that means maintenance of the instruments are going to be a little bit difficult. Second, then the data of geostationary satellite is not very accurate because of the flat viewing angle, because they are above 60 degree north. So that means the geostationary orbits of satellites may not see this area very clearly. And the length of sunlight hours changes very rapidly. For example, from the sun being below the horizon during the 2 winter months to 24-hour sunlight during the summer months. So that means there is a inconsistency in the amount of sunlight received by these places. And also the another biggest problem what we have is the analytical, empirical, stochastic or the other artificial neural network models which we are actually using to estimate the solar radiation. Say for example, when we talk about analytical errors, this is we may have incomplete or missing data of the geostationary satellites. This is possible because maybe there was some solar flare due to which some of the solar batteries malfunctioned or did not function. So that means the satellite may not be getting the data what is required for our analysis. So that may happen. This is a analytical error happening due to the satellite's power fluctuations. And the stochastic model, that means when we are assuming how much the earth receives the solar radiation, our models will not have the presence of clouds. So this stochastic model doesn't know exactly where the cloud is, where the cloud is not. So that means even though we measure, we assume our models can be made to understand the cloud pattern, but due to the change of wind directions, it is not always accurate. So we will have some problems related to the presence of cloud. And also the empirical parameters, like for example, which change from area to area. Maybe Greenland, if you look at, say for example, the altitude of measurement keeps on changing. So that means the sunlight received also keeps on changing. So the empirical parameters of each locality is also quite difficult to analyze. And the artificial neural networks, if you are going to use it for the development, then they do need exceptional computer power. So these are some of the limitations due to which measuring the amount of sunlight received in the Arctic region is quite challenging.